Welcome back. Am I audible? So, in the previous lecture, we started introducing some non-idealities of a transistor. One of the non-idealities that we saw was channel length modulation, and its effect was that of introducing a Y22 or a GDS, right? So, at the almost at the end of the last lecture, we were doing this. So let me sketch only the incremental model. So this is this becomes the, or rather, let me only sketch this part. This becomes the new incremental model of the transistor, right? With the incorporation of GDS. And note that GDS here is not a physical resistor; it's a model resistor. It's modeling the effect of channel length modulation, and the physics behind that was, as you keep on changing the drain voltage, the length of the channel also changes, right? It either shrinks or increases. The length of the channel gets modulated, and since the quiescent current through a MOSFET is inversely proportional to L, or it's dependent on L, which means that as the channel length gets modulated, your current through the device will change, and since this current through the device is now becoming sensitive to the drain to source voltage, which essentially means that now I have some influence of the drain current on, I can influence the drain current by changing the drain to source voltage. And if you basically look into any port and see that you are able to influence the current through the port by changing the voltage across the port, which means that there is naturally a non-zero impedance. And in this case, the non-zero impedance is RDS or 1 over GDS. If we want to express that in terms of conductance, GDS is a preferred way of preferred term to be used. Now, the stuff that you should, we also covered, but you should also remember at the back of your mind is what to neglect when, right? So I'm repeating this from the previous lecture. So unless otherwise mentioned, you can essentially neglect channel length modulation for to figure out the effect of, figure out its effect on the quiescent current, right? So unless otherwise mentioned, neglect channel length modulation for evaluating the quiescent current. Why? Because we are operating under the assumption that the channel length modulation changes the output current. It's slightly. It's not zero. The change is not zero, but it changes slightly. And since we are doing all sorts of approximations, we can as well say that while, for example, if your drain current, if you neglect channel length modulation is, let's say, 1 milliamp, and in the presence of channel length modulation, it changes by 10 microamp, for example, then I can say 10 microamp is much lesser than 1 milliamp. I'll neglect. It eases the calculation by a lot. Then so essentially we'll neglect it. Similarly, we'll neglect the effect of channel length modulation while evaluating the value of GM, right? However, we cannot neglect the channel length modulation when we are trying to evaluate its effect on what? On GDS, right? You cannot neglect anything with respect to zero. So if we are trying to understand the effect of GDS, or if we are trying to understand the effect of the swing at the output and its effect on the current through the transistor, then we cannot neglect it, right? So however, there is a particular case, or there is a case in which you can neglect, and we also we discussed it in the previous lecture, and the case was as follows. Let's say we have a load resistance or a load conductance connected, and the source voltage is grounded. Right. By the way, this is again. Let me talk. I'm sure you all don't know this, but for the sake of completion of all the terminologies, this particular topology is also called a common source amplifier. And easy way to remember, which is, I mean, you will see just like we have common source, we'll have common gate, common drain, and so on. This common terminal, the terminology, instead of common, if you think of it as grounded, that helps in remembering, because it's not always apparent which is common to what, but it is quite apparent what is grounded. So incrementally, whatever is grounded, it's like common that, right? So I mean, the way I remember this is basically it's a grounded source, so common source amplifier. Anyhow, the point that I was trying to make was, in this case, if GL is much greater than GDS, or basically in the resistive domain, if RL is much less than RDS, which is 1 over GDS, then we can neglect the effect of GDS. Right? Under this condition, you can as well neglect the effect of channel length modulation, because the incremental current that will come out of the transistor will not go into GDS. It will prefer to go into the RL. Okay, and you don't even have to do all these all calculations. You can basically look at the Thevenin equivalent output impedance. What is RTH? In the following the arrow that I have shown, is 1 over GDS, right? It's 1 over GDS. So if RTH is much higher, right? Is much higher than RL, then what? You cannot neglect it. If RTH is, let's say, infinity, then the output is dominated by the current times RL, right? So if essentially if the impedance that you are seeing inside looking into the port is much higher than RL, then you can as well neglect it, right? Because the current will not prefer to go into that impedance that you are seeing. Okay, fine. So, but however, if it's the other way around, right? But if RL is much greater than RDS, for example, if RL is tending to infinity, rather RL is an open circuit, what will be the gain? What will be V0? Yeah, so there V0 will be GM over GDS or GM times RDS, right? So this is often called the intrinsic gain of the transistor, right? This is the maximum gain that you can get out of the transistor, right? Do you agree with that statement that I made? This is the maximum gain that you can get, right? Why? Yeah, so it can, because in the absence of GL or in the absence of RL, all the current goes into the GDS or the RDS, and the gain that you get is GM times RDS. If you put anything in parallel, part of the current will get divided. It will be divided between GDS and GL or RDS and RL, and actually the gain will drop from this. So this is the maximum gain that you can get out of one transistor, and this is often called the intrinsic gain of the transistor, which is an important parameter to characterize the transistor. I mean, you cannot have a transistor whose intrinsic gain is say 10, and you decide to make a common source amplifier of gain of 100. That's not going to happen, right? So you have to do something on top of that to ensure that you increase the gain as required, as and when required. We'll see those. We'll look into those topologies later on. So a quick way to understand, and one of the things that when you are characterizing any technology, or when you are trying to understand whether the transistor that has been given to you will serve your purpose to to get amplification or not is also to characterize what is the intrinsic gain of the device. Okay. Okay. Any questions? No. Okay. So again, what is GDS in terms of quiescent parameters? What is GDS? Lambda times IDS. And is lambda user controllable, designer controllable, or lambda is fixed? Is lambda like mu and Cox, you cannot do anything about it, or can you change lambda? You can change or cannot change, right? So if you look back at your notes and tell me I can here. Why did we derive lambda stuff? So what was lambda? Lambda was this guy, right? So lambda was essentially proportional to some constant, proportionally constant alpha divided by the length of the device, isn't it? So now, do you think it can be changed? It can be influenced? Yes or no? Yes, it can be. Pardon? Alpha was a proportionally constant that we assume here, right? So if you change VDS, there will be, the length will change by certain factor, alpha, right? So that was the proportionally constant. That is a function of the device that you cannot influence, right? But this guy comes because you are basically doing, you are taking L common 1 minus delta L by L and doing a Taylor series of that, right? So essentially it becomes a designer controllable variable. So the intuition behind that is what was the genesis of lambda? The genesis of lambda was you have some channel, and this, as you apply drain to source voltage, the length of the channel was getting modulated, right? So the length of the channel was maybe changing, and this delta L as a function of L, right? So your current is proportional to IDS is proportional to L1 minus delta L over L, right? So note that this is delta L over L, not delta L only. So as it depends on the ratio of the change with respect to the original length of the channel, right? If the channel length is, let's say, infinity, then delta L can be finite, but it will not be having any effect on the change in current, right? Does that make sense? Your IDS is proportional to W over L, right? Absolute L, not relative L. If you change that L, if you are effective, if you are able to change the length, right, then the total length then reduces from L to L minus delta L, right? But the current, the change in current will be proportional to delta L over L. If the original starting L or original starting length would have been very large with respect to delta L, then I might as well say that the current didn't change, right? It's almost equivalent to saying I have a 1 meter scale and I'm trying to see what's going to happen if I change how much change in length of the scale I'll see if I make a measurement error of, let's say, 1 micrometer. I mean, you effectively won't be changing the length of the scale at all. However, your starting position of the scale is like the scale is 10 micrometer long and you are trying to see how much percentage of change in scale will happen if I make an error of 1 micrometer, then it's like 10%, right? So it's all a relative game, right? So in this case, your current will, you will not be able to, you will be able to influence the current by a lot if the starting L is high, is small, and if the starting L is very large, then you will not be able to influence the current too much, right? So that's why, as you see that when the technology progresses from longer channel length devices to shorter channel length devices, you see the effect of channel length modulation becomes worse and worse, and which impacts the GDS, which impacts the gain of the intrinsic gain of the transistor. So you will see that some terminologies are often thrown quite often. One is to say that the intrinsic gain of a device becomes poorer and poorer as you go to advanced technology nodes, right? So it's basically saying the same thing as I just now said, that if you go from, let's say, 350 nanometer technology, which has a longer channel length. By the way, this technology, this number in front of the technology refers to the length of the channel, right? When I say 350 nanometer, roughly you can assume that the length of the channel is 350 nanometer. When I say 65 nanometer, you can roughly assume that the length of the channel is 65 nanometer. So as you go from higher technology nodes to lower technology nodes or advanced technology nodes, this GDS becomes worsened because of channel length modulation. Okay. However, one good thing about design is you need to know which things you can control and which you cannot. So when I say I am using, let's say, a 65 nanometer technology node, what essentially I'm saying is you cannot reduce the length of the channel below 65 nanometer, right? Or if I say that the length, if you are using a 180 nanometer technology node, which means that you will not be able to reduce the length of the channel below 180 nanometer. It doesn't say anything about if you can increase the length of the device. You can always increase. You cannot go below the technology limit. So sometimes, if it's possible, you need higher, you need lower GDS, you need higher gain, intrinsic gain. So which means then what is the thing that you need to do? Let's say I want higher RDS. Then what do you need to do as a designer? Increase the L, right? You can increase the L to get better RDS, right? So in other words, in this case, I can say if L increases, RDS increases, right? But can you tell me what's going to happen? I mean, let's say I want to make a common source amplifier whose gain is GM times RDS, intrinsic gain is GM times RDS. I want to increase RDS, so I increased L. What's going to get affected? There are only two things, GM and RDS, right? What's going to get affected? GM is going to get affected, right? So how is GM going to get affected? It will increase or decrease? Decrease, right? Because why? Because your here, right? So clearly, because it's proportional to W over L, 1 over L, your GM is going to decrease, right? So then you don't really get any benefit, looks like. But can we change this? Can we restore the value of GM without changing, without affecting RDS? ID set can be constant. Value of the constant can be different, right? Increase the VDS. GM doesn't change on VDS, right? Depend on VDS, right? So GM is this guy. So we increase L. We can increase, I mean, yeah, lambda would vary. That's what we, increasing L varied lambda. That's why RDS increased. No, I didn't say that. The question was, I want to increase RDS, and we established that increasing L for the same current, right? It's GDS is lambda times IDS. For the same current, if you increase L, your RDS increases. You cannot change current. Okay. So so maybe this is not the right expression for GM if I am trying to evaluate what's going to happen if the current is same. I can use the alternate expression, which gives a better visibility of what's happening, where the current term is there, right? This is for same current or same idea. Okay, so if I what do I need to do now if I want to keep the GM the same? Yes.
So are we including the 1 plus lambda VDS term in the formula of IDS?
No, we are not. As I said, the first order will neglect the effect of lambda while calculating GM and I. Will only, unless otherwise mentioned. Later on, you will see there will be some cases where we need to, but unless otherwise mentioned, will not. So IDS doesn't depend on VDS to the first order. So then what can I do? So in this case, what are the designer control variables? Mu and Cox is no, we cannot change. We are saying that we are doing it for the same IDS. So IDS is not changing. L I am doubling, or let's say increasing. So what remains? W, right? So what do you need to do to W? You have to increase W, right? So to keep GM unaffected, increase W by same factor. So basically keep W over L the same, right? So that is one design choice that you can make when you'll be designing in the later half of the course, and for certain gains, certain this, certain that, then you will see that you need to understand what are the design knobs, right? So in this case, in the example that we just took, there were two design knobs. One was L, one was W, and we saw that. And in this case, we see that there are your incremental parameters behave differently if we change certain design knobs. Okay. So again, at the sake of repeating the same thing over and over again, let me again try to point out the fact that when you will be designing, one part is analysis, another part is design. When you will be designing, you will see that many of the transistors will not behave in the simplistic model that we are using in this manner, like mu and C W over L VGS minus VT whole square. Your transistor will not behave like that, which essentially means that all the GM equations and GDS equations that we will be using throughout the course to understand analog circuits will also not be valid to a large extent. However, the thing that will be valid are the choices of the design knobs. Okay, so what will be valid is that how the GDS will change, which side the GDS will change, will it increase or decrease if you change L? What will happen to GM if you increase or decrease W? What will not be fixed is how much it will change by, right? If your model changes, if your model parameters changes, you will not know whether GM will increase linearly or with the power of 1/3 or with the power of 1/4. That you will not know. Okay, but you will know which side if you change something, which side the current or the GM or the GDS should change. It's equivalent to the analogy of opening the tap. You don't know how much force you need to give to get how much water, right? So, but you still go ahead and you live your life, right, without knowing the maths of it. So same thing here. So you need to know which side you need to turn the knobs to increase something or reduce something, and rest of it you leave it to a simulator. Okay. Okay. Any questions? Okay, fine. So now what we see is that it looks like we have a handle. It looks like we have a handle of even if we have a port transistor which has a 4 intrinsic gain, I can keep on playing this game. Right? Let's say I saw that my intrinsic gain was 10 for a transistor. I want 100. What do I need to do? For the same current, I will increase L by a factor of 10. I'll increase W by a factor of 10. So GM doesn't change. RDS increases by a factor of 10, and I increase the intrinsic gain by a factor of 10. Easy, right? But is there something that we are sacrificing? So that's what we will see next. The stuff that we haven't considered till now is the following. So the effect of, I mean, when we write this current equation, right? What is this Cox? Is the capacitance between capacitance of the oxide layer, capacitance per unit area, right? However, when you are designing, let's say, a common source amplifier, and you say that this is what I have, where does this Cox appear? This is the capacitance, right? This is the capacitance. Between which two nodes does the Cox appear?
It's the oxide capacitance.
Right, it's the oxide capacitance per unit area, but does that have any other impact on your... So by the way, what is this? Why is the MOS transistor symbol like this? What does this parallel lines mean? That effectively is the capacitance, right? It's effective because you have an oxide, and that oxide gives you the capacitance, and the capacitance is essentially between the gate and the channel charge. There will be a channel charge here, and there you will be applying some gate voltage here, and you will be modulating the channel charge here, and that's what gives you the capacitance, right? So in other words, in the circuit, right, in our circuit, where will that capacitance appear? Between, yeah. So basically, what we can say is this: we have, let's say, charge here, and if we influence, so let's say drain and source are connected together. So for the timing, let's assume drain and source are connected together. The transistor is on. By on, I mean the channel is produced, or VGS is greater than threshold voltage. So if that is the case, right? So the capacitance will be it's almost like a parallel plate capacitor. One plate is the gate, and another plate is a channel, right? So what is the capacitance, total capacitance between the gate and the channel? If Cox is the unit capacitance, Cox times WL, right? So this is the C total is Cox times WL, correct? WL is essentially the area of the slab, right? Area of the gate slab. This is correct, but there is some additional terms that comes into picture. I mean, there are a lot of additional terms comes into picture, but we are only concerned about the ones that are major, right? Yeah. So as you see that there will be an overlap between the gate and the drain and the gate and the source regions, and that is done by purpose, because if you underlap, that is, if there is no overlap, there is a chance that the drain doping is, there is slight gap between where the drain doping ends and where the channel begins. Then you will not have in there. Then basically you will have a discontinuity in the channel. The charge might not flow, the current might not flow. So instead of doing that, it's better to overlap a bit, because you cannot hope to be exactly at at that junction. You have to either go, you have to overshoot or undershoot. It's better to overshoot, because if you undershoot, the transistor will not work. So by design, you will have an overlap, and the amount of overlap is not in your control. That again, your device colleagues would have made a device and would have told that for this particular technology, that much overlap you are going to have. Okay, so if that much overlap you are going to have, what is the stuff that is in your control? The stuff that is in your control is this W, right? So what essentially, so that is why this overlap capacitance is often expressed as capacitance per unit W, right? Because the W, if I give you the capacitance per unit W, which is not in your control, but W is in your control, so you can change the value of the capacitance by changing W if required, right? So you will have, yeah, so you will have an additional capacitance. Let's say, let me call it CGD times W. Similarly, you have a capacitance on the other side between it and the source, right? So you'll have CGS times W. This is called overlap capacitance, right? Okay. Okay. So now we are, I mean, this is fine. However, the problem is, for a circuit designer, we don't really have a tapping point in the channel, right? The terminals that we have access to are drain, source, gate, and body, right? We haven't yet considered the effect of body, but let's limit ourselves to drain, gate, and source for the time being. We don't have any terminal in the middle of the channel, right? So what circuit designers then tend to do is to say that we understand there is a channel. Actually, the channel charge gets influenced, but we will split the channel between drain and the source, and we'll say that in this particular configuration that I have shown, half the charge is apportioned to the channel, half the charge is apportioned to the half the charge is apportioned to the source, half the charge is apportioned to the drain. So what we essentially are saying is, if we
are defining the overlapping capacitance per unit length.
Per unit W. Yeah, I mean, unit is length, yes. I mean, here, I mean, length means what? Length means the length of the channel. And what is length of the channel here? This is L, right?
I'm asking that.
Okay, that proportionally constant, CGD overlap.
I think CGD overlap is C of overlap divided by L, right?
Yeah, fine. But the reason we are not getting into that is, you can do a bunch of maths to figure it out, but what will you do with that end product? The end product is not in your control, so you as well use it as a black box and go run. Right? So if you are a device designer or you're a modeling engineer, right, you'll have to then take into account what is the effect of the overlap, how can you change the effect of the overlap and so on. Then you have to get into the details of it. But if you are doing a circuit not in your control, we don't think about things that are not in our control, right? We just take, okay, fine, this is how it is, we'll use it. Okay, so what essentially, how we model, because we do not have a terminal at the middle of the channel, we say that if I change the gate to source voltage or the gate to channel voltage per se, if it is possible, then I can as well say that half this channel charge is apportioned between the gate and the source, and half the channel charge is apportioned between the gate and the drain. Okay. So by the way, the way I have sketched it, the transistor clearly is in linear region, right? Because drain and sources are shorted together, and the transistor is on. By on, I mean VGS is greater than threshold voltage. So this is in linear region. So in linear region, or okay, so let me say in basically when you don't have pinch off, when you have kind of uniform distribution of the charge in the channel, we essentially say that your CGS, that is the total gate to source capacitance, that is this is CGD. The total CGS is half of the channel charge, that is Cox W times L by 2, plus whatever overlap you had on the source side. So CGS overlap times W. And similarly, CGD will be same because there is no distinction between source and the drain when the transistor is in like deep linear region times W. Okay, so they are same. Now, if I increase the drain to source voltage, and let's say we hit saturation and you have pinch off, right? When you have pinch off, how does the charge profile change? So let me sketch here. Let me sketch, instead of now sketching the entire MOS transistor, the device, let me do it in the circuit domain. So your channel charge was initially like this. Now the channel became pinched off. So this became something like this, right? So this is gate, this is drain, this is source. And this is drain. Okay. So when you have pinch off, what can you comment on the influence of the channel charge if I change the gate to drain voltage? So let me ask the question slightly differently. So we have a capacitance here, right? So let's say this is the modeled capacitance, right? This is supposed to be the total capacitance between the gate and the drain. That is the channel capacitance due to overlap and capacitance due to the channel, right? So if that is the case, and let's further make an assumption that the overlap capacitance is very small. Okay. So then can you comment on if I change the gate to drain voltage, that is, let's say I put a battery between gate and drain, and I change the gate to drain voltage, will you be able to change the channel charge? Why will it change? Can you change the channel charge by changing the drain side in saturation? Why? I'm not including channel and modulation, by the way. Without channel and modulation.
You are increasing the drain voltage.
Right.
So naturally, it will be expecting more charges towards in the end.
Okay, let me ask you in this way. If I increase the drain voltage, will there be any change in current? No, right? So there's no change in current, means there's no change in charge, right?
There would be an incremental change.
Will there be any incremental change in current? No, if I change the drain voltage, let's say I incrementally change the drain voltage, will there be an incremental change in current? Without channel and modulation? No, right? There will be no. See, essentially you are unable to influence the channel by changing anything on the drain side, right? So you don't have control over the channel by changing anything on the drain side, which means that there is no effect of capacitance. This capacitance you will not be able to affect the capacitance between the gate and the drain. So the contribution of the channel on the capacitance on the gate and the drain is essentially vanished. Okay, so in saturation, that is why in saturation, CGD becomes only CGD overlap times W, which is the physical capacitance that is present. The one because of the channel vanishes. Okay. However, if you go to the CGS, right? If you go to CGS, will you be able to influence the channel charge by changing the gate to source voltage? Yes, right? I mean, that is essentially what the transistor action is, right? You should be able to influence the channel charge and thereby the current by changing the gate to source voltage, which means that the entire effect of the capacitance now gets shifted towards the source, towards the gate to source, right? So what it was initially apportioned between drain and source, but now it got shifted to entirely to the source side, right? But now the profile, the charge profile is not a rectangular profile. It's a triangular profile. So the capacitance that you see is no longer Cox times WL. It's some factor, right? So, and as it turns out, you can do the math, the factor comes out to be 2/3. So this becomes 2/3 times Cox times WL plus the overlap capacitance, which anyway is a physical capacitance which is present, times W. Right? So in saturation, this becomes your capacitance, the effect of capacitances. And again, like if I give you some numbers, as it turns out, the overlap capacitance is generally much smaller than the channel capacitance. So generally, this Cox times WL is much larger than CGD overlap times W. So this is how the devices are, right? So, I mean, there's no physics behind it per se. I mean, there is physics behind it per se because of the size of the device, but devices are made in such a way that these overlap capacitance are negligible. Because ideally, they should be zero. There should be no overlap. We are having slight amount of overlap to ensure that the channel, we don't cut off the transistor action. But having said that, it's not a big portion of the total capacitance. However, you cannot neglect this overlap capacitance from the gate side because then it goes to zero, right? You cannot neglect anything with respect to zero, right? So that is why on the source side, often you will see that the total capacitance is expressed as this. Is that the biometric? This doesn't go up, is it? Or will it go up after some time? Keep it outside, maybe. So, yeah, continuing the thought. So essentially what happens is we restrict the gate to source capacitance to the channel capacitance and not the overlap capacitance. We don't include overlap capacitance because basically it makes life easy, right? It's not about trying to figure out what the capacitance will be to the 5th decimal place, but to have a rough idea of what is the dominant one. If we have a clear dominant winner, we stick to that, right? Okay, fine. Any questions? Okay. The 2/3 term comes because this is no longer flat, right? If this is a perfect parallel plate capacitor, this becomes this area times C of unit area times the area. Right? But if this is not flat, if this is like triangle, then it will go up by some factor. So one way to think about it is, you have to find out the center of gravity of this. So if you do that, then that 2/3 comes. Okay. I mean, having said that, it's not as if when you are designing a device, you have to plug in those values of 2/3 Cox and all. They'll be given to you. All you need to understand is that how CGS will vary if you change W and L. Right. So that is in your control. So you need to vary that. You will be given the unit values, but then when you scale, you need to understand how does the total capacitance scale. And why is it important to us? It is important to us because we saw that in order to increase the intrinsic gain of the device, what did we need to do? We had to increase both L and W. Right? Yeah, by the way, the intrinsic gain is a DC parameter, right? It's a very small signal. It's a small signal DC parameter. When I say DC, what I'm saying, I'm neglecting the effect of any capacitances anywhere, right? So GM, GDS are DC parameters, and you can influence them by changing L's and W's. But at the back of your mind, you should also understand that when you change L and W's, you are also affecting the capacitances, right? So in the example that we gave, if I have to increase the gain, intrinsic gain of the transistor by a factor of 10, I have to increase the L by a factor of 10, and I have to increase W by a factor of 10, which means I make the device 100 times bigger. When I make the device 100 times bigger, what is happening? CGS is increasing by a factor of 100. Correct? So what are the, I mean, then we have to stop and think whether this is feasible or there is some, I mean, are we seeing some effect? Okay. So that's what we will see next. So let's sketch our common source amplifier once again. So CGS is basically this capacitance. CGD is this capacitance. Okay. There is one more capacitance that I haven't talked about till now, and that capacitance, is time to talk about that. And that capacitance is the capacitance between the drain to body. Okay. So when I say drain to body, what do I mean? Again, this is so this MOS transistor is built over some p-type substrate. So which essentially means that, I mean, you will have a p-type connection somewhere here, which is, let's say, is grounded. So this is N, this is P. What can you comment on the bias? Is it this is the PN junction, right? This is the PN junction. So do you want it to be forward biased? Do you want to be reverse biased? You clearly want it to be reverse biased. So if you have a reverse biased PN junction, there is a depletion region associated with it, which means there is a depletion capacitance associated with it, right? So essentially, you'll have a depletion capacitance associated with this. Similarly, I mean, there will be a depletion capacitance associated between the source and the body also. Let's say this is also P plus grounded, so you can have a depletion capacitance between this. So essentially, what I'm saying is there is a capacitance between, this is body terminal, right? So there is a capacitance between the drain and the body, and source and the body. In the transistor symbol that we have used till now, we haven't used the body terminal till now because it was not necessary. But looks like now it has become necessary. Body in general is grounded always, right? So essentially, if I take out a fourth terminal and connect it to the ground, because our p-type substrate is almost always grounded, which essentially means that the body to source capacitance is not in play, right? In this particular configuration, in the common source amplifier, the body to source capacitance is not in play because source is grounded, body is grounded. Even though there is a capacitance, it is inconsequential. However, the drain to body capacitance is in play because drain is swinging, right? You're taking the output from the drain, so drain voltage can change. However, the body is grounded, which means you have a capacitance. The capacitance between drain and body cannot be neglected. So you'll have a CdV capacitance between drain and body. And since body is grounded, we often say that the CdV is between drain and ground, right? Instead of taking another terminal out, we say that this CdV is between drain and ground. Okay. Okay, so your incremental model of the transistor now has become this. We started off with this. So the incremental model has now become slightly more involved. Now we have a GDS. This is gate. We have a gate to source capacitance, CGS. This includes the overlap capacitance and the channel capacitance. You have a, let me use a different color for capacitances here. Then you have a gate to drain capacitance. Then you have a drain to body capacitance, which is, okay, let me ground this. It's better to ground. Similarly, you will have a source to body capacitance also. Okay. Okay. So now we'll have to see what are its effect in our circuit. Yep. So fortunately, in case of common source amplifier, many of these capacitance are referred to ground. We don't have to worry about many of them, but for some of them we cannot but worry. Then we'll have to analyze their effects. So let's see. So if I replace the incremental model of the common source amplifier, this is what we get. So we had this coupling capacitor, right? Let me call this C1. And this was the gate terminal. This is VG. Source is grounded. Now we have this guy CGS. And we have this guy CGD. And we have this guy CDD. And let's not think about GDS for the time being. And this is, let's say, RL or RD in this case, the way I have sketched. And we also have another one, right? We have this one, this R1 parallel R2. Okay. So now we'll have to see what is the effect on V0. So till now, when we neglect the capacitances, the V0 was independent of frequency, right? So the earlier model would have worked for even infinite frequency, no problem. But now you see that in reality, when the capacitances come into picture, there will be a frequency limitation because capacitances are frequency dependent impedances, right? So your impedances will change, which means the voltages and the currents at various junctions will change, through various nodes will change. Then we need to evaluate what is the effect. Okay. So let's do it part by part. So let's simplify stuff. Then we'll put things together. So even though this is not a correct thing to do, but we will neglect CGD to start off. Why? Because as you see that it seems like I can have, if I neglect CGD, I can evaluate two halves of the circuit independently, right? So this is one half, this is another half. And how are they communicating with each other? They're communicating with each other through the control source, GM times VGS. And the output side is only dependent on the input side if we neglect CGD. However, if I have CGD, there is an effect of output coming back to the input. It's equivalent to the case of Y12, right? So this particular contraption, for this particular contraption, Y12 is not 0. Do you see that? What is Y12? Y12 by definition is the short circuit current at the input terminal if you change the voltage at the output terminal, right? So clearly if you short the input terminal and change the voltage at the output terminal, now there is a current, there is a possible, there is a path from the output to the input through CGD, which means your Y12 is not 0 anymore, right? So this is not that good transistor, good characteristics that we started off with, right? So having said that, I mean, one thing we'll see how to deal with this, because moment you have coupling between multiple parts of the network, you cannot isolate your analysis, right? But if you cannot isolate your analysis, the math becomes involved, it's difficult to get intuition. So what we generally try to do is to simplify, one, at the risk of being erroneous. So what we will do to start off, we'll say that CGD doesn't exist. Let's see what happens. Then we'll put back CGD and see what happens, and then club things together. Okay. So to start off, let's neglect CGD. If we neglect CGD, for the purpose of an analysis, life becomes very simple. And we can essentially say that I will analyze this block first and find out VGS, and then use that information to analyze the second half, right? Analyze the output side of the transistor. Okay, so let's do the first half. So let's neglect CGD to begin with. By the way, this is not an accurate thing to do, but we are doing this with the knowledge that this is an inaccurate. We'll put back CGD later on. Fine. So we need to now find out what will be VG or what will be VG over VI essentially, right? We need to find out what will be VG over VI ideally, right? So now since we have some frequency dependent elements here, so let me ask you one quick question. So let's say I have a transfer function H of S. Now let me put H of j omega. Okay. And I apply an input sine of omega naught t. This is a voltage to voltage transfer function, right? So in other words, what I'm saying, if this is VI, this is V naught. So V naught j omega by VI j omega is H of j omega, right? So what will be V naught if input is sine of omega naught t? Note that this is a phasor domain. This is phasor. There is no information of t there, but I am applying a time domain input of sine of omega naught t. Can you tell me what will be the output? Mod of H of j omega or some omega naught, and then sine omega naught t plus some phi. What is phi? Angle of H of j omega naught t. Great. Okay. So since we all understand this, we can fast track. So if this is the case, this directly, by the way, before again, even though this is not relevant to this course, but let me, for the sake of completion, let me ask you this. What assumption did I make when I wrote the transfer function? It's LTI. right? So if you, the assumption that I made was if an input is at a frequency omega naught, output has to be at a frequency of omega naught. It cannot be of any other frequency. So that is why if input is at, we didn't bother about, even though the input had a frequency of omega naught, whether the output, we didn't have to think whether the output frequency will also be at omega naught. Had this been a non-LTI system, then this wouldn't be obvious. Okay, because this is an LTI, this becomes obvious. Great. Okay, so now the question becomes, how do I mean, what will be the transfer function of this guy? What will be VG over VI, right? So we can calculate the VG over VI, definitely. We write down the Laplace equations and all. So why don't you do that? I mean, can you tell me what will be VG over VI in this case? Find out VG over VI. And express it in this form, right? Express in, okay, I mean, express in whatever form you want. Okay, can you, one of you tell me what expression that you got? Let's do the denominator first. Can you tell me in terms of SS square plus S, that one? I mean, so it will be easier to club things together. Yeah. R2, RS, C1, CGS, okay.
Plus you have the R2
And the numerator? Okay, fine. This seems correct. Can anyone else corroborate? Okay, fine. So let me take this one. So by the way, the symbols likely change when we go from time domain to phasor domain. Symbols become like capital V, small g, and within brackets S, just to remind ourselves that this is not in time domain anymore, right? Okay. So now this clearly looks to be not a very intuitive thing to analyze, right? We have second order equations. We have how many poles? 2 poles, 1 zeros. So question is, do I need to resort to simulators, or can I get some intuition out of this, right? So we'll do it 2 ways. In the next class, we will see how we break this down in whatever time we have in this class. What I wanted to ask your attention for is, if I look at the circuit and let's see if we can get some intuition out of it, right? So firstly, what do you think is let's start with the numerator term. What is the effect of the numerator term? In terms of at which frequency is it affecting the most? DC, right? So what is the gain at DC? It's 0, which means that it shouldn't be able to pass DC, right? So that clearly is visible from our circuit. I don't have to do much, right? From the circuit, I can see that if Vi is a DC, the capacitor C1 will block the DC and nothing will come to the output. So that part checks out. We have 2 poles. Why do we have 2 poles? Can we make a judgment looking at the circuit whether you have 2 poles or not? 2 poles, 1 pole, 3 pole. Yeah, true, but it's not actually the number of capacitors, right? I can have n number of parallel capacitors, right? So doesn't mean that it will be an n pole system. Yeah, it's basically that's actually the right thing. It's actually the power of S. So in other words, you can say that how many independent differential equations you can write, right? The number of independent differential equations you can write is essentially the power of that system. And whenever you write one differential equation, the solution always has some initial condition associated with it, right? So which essentially means that it's easy to figure out from looking at the circuit that how many initial conditions you can have on the memory elements, in this case on the capacitors. How many independent initial conditions that you can have will determine the order of the circuit. I mean, if you have two capacitors in parallel, you can have only one initial condition, right? Even though you have two of them in parallel. So both of them club together and the order collapses. But in this case, I can have two independent initial conditions, one across C1, one across CGS, which means the order is 2. If we didn't have RS, if let's say RS would have been 0, how many independent initial conditions would you have? 1. Then the order would have collapsed to 1. Okay. So that, I mean, that checks out. It is supposed to be second order system. We have S square terms to the denominator. All good. Now, the question is, can I get an intuition? And it's easy to get an intuition for a first order circuit. It's not that straightforward to get an intuition of any higher order circuit. So whenever we think about intuition, our mind should go and try to figure out, can we break this stuff down into first order circuits? Can we make some assumptions to break it down to first order circuits? Now, as a designer, we know that, why did we put C1 there? What was the purpose of C1? It's only DC blocking. It's supposed to pass almost everything that other than DC is supposed to, right? So C1 was supposed to be infinitely large. And then we figured out what was the constant on C1. But having said that, C1 is supposed to be really large. What is the expectation on CGS? It is supposed to be very small. Why? Because let's assume CGS is large, then what is it that is getting degraded? What will degrade? Yeah. So in other words, let me, instead of putting everything together, let's say that C1 doesn't exist. Let's say C1 is 0 in the incremental sense. And this is what you have. If input is, let's say, sine omega naught t, if CGS increases at the frequency of omega naught, what can you comment on the amplitude that you will see at VG? This is what type of filter? This is it's a high pass filter, low pass filter. How do you know whether it's high pass filter or low pass filter? Yeah, so let's say, like, if I go to infinite frequency, what will be VG? It will be 0. If I go at 0 frequency, what will it be? Right, almost sine omega naught. I mean, you have R2 by RS. That's a division ratio. But at very high frequency, RS goes VG goes to 0. At very low frequency, you get whatever you are supposed to get. Right. So this is what type of filter? This is a low pass filter. Right. Good. So this is a low pass filter. So which means and ideally, what do we expect in a good transistor, in a good common source amplifier? What do you expect VG to be? Attenuated version of input or the input itself? The input itself, right? Without any low pass effect, right? So ideally, we would expect the CG to be much smaller. What is much smaller? Again, we'll have to define. But we expect CGS to be 0, ideally. But we see that it's a fact of life. You cannot have CGS to be 0 because of reasons that we talked about right at the beginning of this lecture. But we know that C1, we expect C1 to go to infinity, and we expect CGS to go to 0. This is our expectation. I mean, that doesn't mean that just because I expect $1 million, I'll get it. Right? So, but we can actually shoot for it, right? And see what are the constraints. So if C1, the reason we are doing all these things is because, as I said, we would like to see if we can break things down into a bunch of first order circuits. Okay. So in a first order circuit, we always associate time constants with a capacitance, right? So if we associate a time constant with the capacitance C1, we would expect the time constant to be really large. And if we And if we associate a time constant with respect to capacitance CGS, you would expect the time constant to be really small, right? So in other words, what we can say is that, okay, so even before going there, what I can say is that if the circuit is supposed to work properly, then this capacitance is supposed to be, the C1 is supposed to be acting as a short circuit, and CGS is supposed to be acting as an open circuit under the proper regime of operation, right? So this is the expected operation regime. So if I simply sketch, and if we have to sketch an intuitive plot of mod of V0 over Vi with respect to omega, right? What do we expect this to be? At 0, what do you expect this to be? No, so I am now sketching the plot for this guy. At 0 frequency, what do I expect Vg to be? 0, right? So it's supposed to be 0. At very high frequency, what do I expect Vg to be? Also 0, because of CGS. Somewhere between these zeros at very high frequency and low frequency, I expect to get a common source amplifier kind of response, right? So this is expectation. This is by no means this is what the transfer function is. This is expectation. We are expecting somewhere in the middle of these two zeros, your transfer function, we expect this to be what? Value. What do I expect this value to be? No, we don't want it. It would have been 1 if R2 would have been infinity. R2 is not infinity. So what do we expect this to be? We expect this to be R2 by R2 by Rs, right? So this expectation is R2 by Rs. And since this is a second order circuit, we expect 2 poles. One pole should be, so this guy is increasing. This guy is increasing in frequency. One pole is supposed to flatten it out. Other pole is supposed to pull it down. So we expect one pole somewhere here, and we would expect one pole somewhere here. And can you tell me whether the expectation of these poles are, do we expect these poles to be nearby, or we expect these poles to be far apart? We expect these poles to be far apart. If they are not, we have to change the design to make sure that they are far apart, because otherwise our design will not work, right? Okay, so in the next class, we'll see that, I mean, how does this intuition lead to the values? And we also massage the equation that we got and see that how these two, intuition and the maths tally, right? Okay, thank you.